Here's a demo of MicroDOS on my 1802 system. I'm going to boot by typing L. It comes up at that point. It does offer a help system, which is pretty nice. Some of the information's on the web too as to how this works. But in any event, I'm going to show you one of the utilities. It's called Examine, or Exam for short. And I'm going to exit from this and then type Exam. It's a disk examination program. And I can start by asking it to do a physical examination on drive 0, very first sector, which shows some of the directory entries. And you can go ahead one sector at a time or back. More directory information showing here. I'm going to exit here. And it's still not fully functional because I've noted that in order to run a format, you do that through the format command. And it launches another program. It's loaded into memory. And at this point, the defaults are the second drive, one-sided, 70 tracks. If I type F to go ahead and format, it gets stuck at that point. Now, it shows here an error, but if I look at my system behind me, the drive light is actually lit still. The Q LED is on. And that's about as far as it goes. I can quit from here, but with that second drive active, I've discovered that MicroDOS won't take any further commands. So at this point, I have to start from the beginning again. So what's going on with format? That's where I'm going to examine next. So what's going on with the format program? Why is it hanging? I don't know, and it could be something with the UT71 program that I got loaded first into the system. It has a number of utility calls that get called upon by other programs, and it took some doing to get that going because, well, number one, it was written with the assumption that it would be running from a ROM image, read-only memory, and I don't have that on my 1802 system. So I had to load it into RAM, and that actually presented a bit of problems because there's a few operations that occur in the program that rely on the fact that it can't write to memory when it's running, and so I had to hack around that to get that to work. So I don't know if it's an issue with the UT71 program, or I don't know if it's something else going on with my system. Again, it's not a system that I bought. I basically made it from a bunch of printed circuit boards, and I relied on other designs from the past that I've looked at and studied. So who knows? But this is the format program in its raw state. It exists as a binary image on a disk, and I was able to write basically a Perl program that reads this in as a binary file and gives me two artifacts. One is this hex dump showing me what's on there. I mean, this is the code that's actually running, and to any person it looks like a bunch of gibberish. I mean, but to the computer understands it. Now, well, the other thing that the Perl, here's the Perl program basically, where I give it the name of the file, and then I mean, this is basically a very poor man's version of a disassembler. Disassembler takes this data off to the right here as part of the file, attempts to make sense out of it. This is assembly programming, and when you write assembler, you're essentially one very small level above machine code. The assembler gives us humans the ability to write programs that instead of actually coding operations as bytes, we can give it a little bit of English-like instructions using symbolics, such as loading of a register, loading and advancing, so forth and so on. So what this program here does is it reads through this, and it basically attempts to decipher what's going on. It's not perfect though, because some of the stuff down here, as you can see, this is actually English. This is part of the prompts and the text and the error messages that all show up when the program's running. This is not necessarily code. This is actually text strings that get displayed as part of the formatting operation. So I can't necessarily take one of these bytes here and automatically assume that it's going to be an instruction. In this case, it's actually text. So it's not foolproof, this disassembler. One of the things it spits out is over here. This is its attempt to disassemble the code. Now, I've gone through here and I've edited it and made some sense out of it, and that's kind of something that I guess one of the reasons why I'm recording this is to show you that, you know, one of the hobbies, I guess, you know, just as some people do those puzzles where it's either crossword or Sudoku or I don't know, I can think of a number of things that people spend their time keeping their brain engaged. I found that I have kind of a interest in understanding and deciphering what this code's doing. So I've gone through here and applied some English labels as I'm going along, just to, you know, provide some context to me what the program is doing. And when the nice thing about writing your own disassembler is that you can customize it to your liking, to the point where, as you can see, here's each byte that it's going through, but this is the ASCII equivalent, what you and I would see as a character or a number. So you can go through here and, you know, it's going to attempt to make this a computer instruction, but if it comes across some text, that's when some of the instructions that it calculates are kind of crazy. And for instance, here's a situation where this is actually the initial greeting that the program does when it starts up. But prior to this editing here that I did, it was taking all these bytes and it was turning it into instruction code above, which if you took it as a regular disassembler output, you'd see a bunch of instructions that wouldn't make sense. So the context of displaying the ASCII characters here gives me a clue as to whether or not this is instructions I'm looking at or if it's text. You know, here's some new lines basically being displayed. So again, it's sort of interesting to figure this stuff out. You know, I'm having fun doing it, and you know, I'm not spending millions of hours on it, but I guess in cumulative time, it's something that just, whether it's used or not is another deal. I'm just having fun doing it here at that point. And some of the things that I've been doing as I go along is adding more and more notation to what it is that I'm, you know, deciphering at this point. Again, it may lead me to figuring out why the format program isn't working. It could be that it's not working with my hardware. It could be that it's not working with the UT71 program in a nice way. It's hard to say. There's a few things that I'm dealing with here, in the sense that, you know, my program is running on a system that wasn't around when this program was written. It's almost 40 years after the fact. It's the system that I'm running is running much faster. So some of the activity in here might be based on assumptions that it was running on a slower clock speed than it was today, although I doubt it. I think what I'm dealing with more is an issue with, you know, how I had to change the UT71 program, and the fact that I'm not running UT71 from ROM. And I don't really want to carve a 2K ROM space in my system just to run one single program. I'd rather try to go down the path that I'm going and go at that point and see if I can get it to work. So we'll see, but at least you're getting some insight into something that I like to do, you know, just as a puzzle. You know, it's kind of fun. You know, this software was written back in the 80s. I was in high school at the time. The actual code, the source code, to my knowledge, doesn't exist anywhere. So in a way, I'm performing an archaeological function by deciphering what was written. And the neat thing is too, I'm learning some interesting ways that programmers back then coded, simply because they didn't have resources like we have today. This system that I'm working only has 64K of memory. That's a grain of sand compared to the amount of memory some of the systems that I work on today have. So they had to make do with the limited resource space. And last night I was up rather late because I came across this little thing here. This is what I'm trying to point out, and this is one of the main reasons I'm putting this video out here, is that maybe if somebody sees this, they'll understand what it is that I'm talking about, and maybe they can point me in the right direction here. But here's a situation where they're issuing a prompt where they're saying, what do you want to do? Do you want to format? Do you want to change the defaults, print the defaults, set the defaults, or quit from the program? So they type this prompt out, and then they wait for the response, okay? This is where it gets a little interesting here. This is an exclusive OR operation on the immediate byte that follows. So they get the value, they get the character that somebody entered here, and they start running tests on it. So this first one's quite, understandable as to what it's doing. It's checking to see if it's an F. But after that point, it starts looking at different values, 5, 13, and 1. Now, these values here don't have anything to do with the ASCII equivalence of that, but I started writing out what this is doing, and it's kind of interesting that with just a few simple instructions, they're able to run throughout the 5 different possible values, and then essentially coming out with an error if it's not the correct value to enter. I think in this case it ignores it, goes to 4B, which is the main menu. So I mean, just in terms of me doing an edit function here, I can basically put that down here, and knowing that if it doesn't pass this test, it just goes up to the main menu. So it basically ignores what the person types unless it happens to be one of those 5 values here. But this method of doing exclusive ORs and how they came up with 5, 13, and 1, that's an area of mathematics and computer science that I didn't really get too much into in the past. I'm gonna figure it out just for my own interest, because I think it's kind of neat. So that's all I wanted to show you today. I hope everything's going well with you, and we'll meet again. Bye-bye.